All right, so in the previous couple of examples, we did applied optimization problems that kind of had a geometric flavor to them. In the first example, we had this two-dimensional geometric problem where we were trying to maximize the area of a rectangle. And then in the next video, we had this three-dimensional geometric problem where we were trying to either maximize the volume of this box or minimize the surface area of this box. And while the calculus was different, they might have felt kind of similar in that they both fell into this broad category of geometry problems. But I think what you'll find with applied optimization problems is they're not always geometry problems. And if I only show you examples of geometry problems, then when you see non-geometric problems in your homework, you'll probably get really confused. So what I want to do to finish up this section is give you one more applied optimization problem, but one where you're not building a two-dimensional square or a three-dimensional box. One where you're trying to minimize time. So remember, when you're reading through these problems, often the hardest part is just getting started. And the way you can get started is look for key words like most or least or maximal or minimal or something like that. If you read through this problem really carefully, I think the key word that you'll find this time is the word least. What's going on in this problem is we're starting over here at point A and we're walking along a trail to point B. And then when we get to point B, we're going to get off the trail and walk across the sand here to point C. We want to go from point A to point C. However, we don't want to just walk directly from point A to point C because all of this is, I don't know, some big desert or something, and we walk really slowly on the sand. In fact, we only walk 3 miles per hour on the sand, but we can walk 5 miles per hour on the trail. So we want to stay on the trail for most of our journey, but eventually we have to walk on the sand because we want to end up at point C. That's where our campsite is or something if you read through this problem. What makes this problem hard is we don't know where point B is. We don't know how long we should stay on the trail before heading off onto the sand. So even though point B is pictured right here, we really don't know where point B is. Think in your head, either we can walk on the trail for a little bit and then cut over on the sand for a long time, or we can walk on the trail for a really long time and then cut over on the sand and we're not spending as much time on the sand, or something in between where we walk on the trail for a little while and then cut over, spending the rest of our journey on the sand. We don't know where point B is, so maybe it makes sense to represent the distance from point A to point B with a variable, like the letter x. Because we don't know where point B is, we also don't know how long the distance from point B to point C is. So maybe we can represent that with another variable, maybe the letter y. As is typically the case in these applied optimization problems, we have two different variables, the letters x and y in this case. What we're trying to figure out is what is the least amount of time it can take for you to get from point A to point C. So that's really confusing because x and y both represent distances, but the question is in terms of time. So to be able to solve this problem, you'll have to be comfortable with the connection between distance and time. This might be a formula that you've seen before. Distance is always equal to rate times time. That's not specific to this problem, that's always the case. If you're driving 50 miles per hour for 4 hours, you've gone a total of 50 times 4, or 200 miles. Distance is just rate times time. When you read through this problem, this keyword least is telling you that that's the function that you want to optimize. So in this case, the function that we want to optimize, because we see the word least, we know that optimize means minimize in this case, is the time of our journey. We have these two different variables, the letter x and the letter y, and our goal is to be able to write this function in terms of those two variables, x and y. And that's not easy at all, but I think it's possible. I think we can come up with time as a function of both x and y, and then maybe we can use some constraints given in the problem to rewrite either x in terms of y or y in terms of x to change this from a two-variable function to a one-variable function so we can take the first derivative and figure out the critical values. We define the variable x to be the distance from A to B, and we define the variable y to be the distance from B to C. Can we use x's and y's to come up with an expression that tells us the total time of our journey? Well, sure. If distance is equal to rate times time, then if I divide both sides of this equation by rate, I get that time is equal to distance divided by rate. So the total amount of time that I'm going to spend on my journey is the amount of time that I spend on this leg of the journey plus the amount of time that I spend on this leg of the journey. The amount of time that I spend on this leg of the journey, well, let's see, I'm covering a distance of x and I'm traveling at a speed of 5 because I'm on this trail. So d is equal to x and r is equal to 5. The amount of time that I'll spend on the first part of my journey is x divided by 5. What about the amount of time I'll spend on this part of my journey? Well, the distance of this second half of my journey is y, And the rate, the speed of this second half of my journey, because I'm walking on sand, is 3 miles per hour. So d is y, r is 3, t is equal to y divided by 3. The total amount of time that I'll spend on my journey, written as a function of the variables x and y, is x divided by 5 plus y divided by 3. It's not obvious at all. You could argue that it's the hardest part of these problems to define your variables and to set up your function. The assumption is not that you could do this on your own, it's that you can watch me do this the first time through so that when you see something similar in the future, you have some examples to fall back on. So thinking big picture, where we are right now is similar to where we were at this stage. We have the function that we want to optimize written in terms of two different variables. Our goal is to use the constraints of the problem to rewrite that function in terms of just one variable. What are some constraints in this problem? What's the extra information that we have not yet used? Well, we're told that point C is 10 miles east and 4 miles north of point A. So assuming straight down means south, the distance due south from point C to this trail, which we're going to assume goes east-west, is exactly 4 miles. The length of this side of this triangle is 4. And because point C is 10 miles east of point A, the distance from point A all the way over here to the point due south on the trail of point C is equal to 10. It's hard to know where to go from here, but if you think about what our goal is to rewrite this in terms of just one variable. In order to rewrite this in terms of just one variable, I need to come up with an equation that relates together x's and y's. Can you think of a way with the numbers and letters that you see in this picture to relate together x's and y's? Well, we do have this triangle right here, and it's a right triangle, so maybe that's a hint that we should use Pythagorean theorem. What the Pythagorean theorem does is it relates together the lengths of the legs of the triangle and the length of the hypotenuse of the triangle. We know that the length of this leg of the triangle is 4, and the length of the hypotenuse of the triangle is y. And if you get kind of clever, maybe you can represent the length of this leg of the triangle in terms of x. Because if you could represent the length of this leg of the triangle in terms of x, Pythagorean theorem would produce an equation relating together x's and y's. And because we know it's 10 miles from here to here, and x of those miles are from A to B, the remainder, in other words 10 minus x, is the length from B to this point right here. Using Pythagorean theorem, a squared plus b squared has to be equal to c squared. Playing the role of the a is this length of the triangle, 10 minus x. Playing the role of the b is this length of the triangle, 4. And playing the role of the c in the triangle is the length of the hypotenuse, which is y, so we get y squared. The constraint in this problem is that 10 minus x squared plus 4 squared has to be equal to y squared. That's not obvious at all. And it's probably the hardest part of the problem. But if you can get this far, if you have your function in terms of two variables and a constraint that relates together those two variables, I think you can finish the problem. If you're feeling brave, go ahead and solve it from here on your own. If you're not, maybe you can watch me do it. What you would want to do is take your constraint and solve this for one of the two variables. It doesn't matter which one you solve for, whichever one you prefer. It's probably easier to solve it for y, so maybe I'll take the square root of both sides of the equation and get that y is equal to the square root of 10 minus x squared plus 16. That 16 being the 4 squared. Note that I cannot cancel out this square root and this square, for example, because I have two different terms underneath the radical. This doesn't simplify nicely. Also note that when I take the square root of both sides of the equation, I should put in a plus or minus here, but the negative solution doesn't make any sense in this context because I'm talking about the length of the hypotenuse here, and the length has to be positive. I have y written in terms of x, so I can return over here to my function, and I can rewrite my function, not in terms of both x's and y's, but only in terms of x's, because I can replace all the y's with this expression. The total time my journey will take as a function of x is x divided by 5 plus the square root of 10 minus x squared plus 16, all divided by 3. It's not the prettiest thing in the world, but when you get good at these, you'll look at this and think that it's absolutely beautiful because all the hard work is done. I now have a one variable function. So it's no longer, in a sense, new applied optimization stuff. It's old optimization stuff. It's the stuff I learned in the previous section. Take the first derivative, set it equal to 0 to figure out your critical values, and you're done. You can take the derivative of this thing the way it's written right now. I probably wouldn't. I'd probably rewrite this first term as 1/5 times x, and then rewrite this next term as 1/3 times something raised up to the 1/2 power, because when I take the square root of something that's the same as raising it up to the 1/2 power, instead of leaving that something as 10 minus x squared plus 16, I'd probably expand these parentheses, so figure out what 10 minus x times 10 minus x is, 100 minus 20x plus x squared, and then combine like terms, so the 100 and the 16 will go together, and what I think you'll end up with is x squared minus 20x plus 116. So unfortunately I screwed up. Maybe you caught it. I wrote a 3 right here, and then I changed that into 1/2. I said 1/3 in the video, but I wrote 1/2, which messed everything up. So I had to go through and erase a whole page down here, and here I am re-recording stuff. Anyways, instead of dividing by 3, I'm going to have 1/3 as the coefficient. I now have my one variable function in a form that's conducive to our derivative rules, so I'm going to figure out the derivative, t prime of x. I need the derivative because I'm trying to find critical values, and critical values come when the first derivative equals 0. So the derivative of a sum of two terms is just the sum of the derivatives. The derivative of 1/5 x is just 1/5. That's easy. The derivative of the second term is kind of a mess. The 1/3 is a coefficient, so I'll leave that alone. And then I'll take the derivative of x squared minus 20x plus 116 raised up to the 1/2 power. For that, maybe you're thinking chain rule. The outer function is the stuff raised up to the 1/2 power. So I'll bring that 1/2 down in front, and my new exponent will be 1 less than that 1/2. In other words, negative 1/2. And since I'm using the chain rule, I leave everything on the inside completely alone, x squared minus 20x plus 116. But then I'm not done. I have to multiply by the derivative of that inside function. The derivative of x squared minus 20x plus 116 is 2x minus 20. Our goal is to take this derivative and set it equal to 0, which is going to be kind of a pain the way it's written right now, so it might be worth spending one extra step cleaning this thing up. I'll leave the 1/5 alone for now, but instead of 1/3 times 1/2 times all this stuff times 2x minus 20, I can put the 2x minus 20 up on the top of the fraction, and then down on the bottom of the fraction, the 3 and the 2 from 1/3 and 1/2 make a 6, and then instead of x squared minus 20x plus 116 to the negative 1/2, I can write x squared minus 20x plus 116 to the positive 1/2 if I put it down on the bottom of this fraction. I got my first derivative, which I want to set equal to 0 to figure out my critical values. So I'm trying to solve the equation 0 equals 1/5 plus, maybe I'd cancel a 2 from each of these terms up in the numerator with a 2 from this 6 to make it x minus 10 divided by 3 times all this stuff to the 1/2 power. And since I'm going to be doing algebra, maybe I won't leave it in exponent notation. I'll instead switch it into radical notation, as that might be a little bit more conducive to what I'm about to do. The real challenge with solving this equation is the radical, so maybe I can isolate this radical and then square both sides to get rid of it. The way I'd isolate it is maybe first get rid of this 1/5, so subtract 1/5 from both sides of the equation. Then get rid of fractions by doing a little cross multiplication trick, where I multiply both sides of the equation by 3 times the square root of x squared minus 20x plus 116, and then multiply both sides of the equation by 5. And what that'll give me is negative 3 times the square root of x squared minus 20x plus 116 equals 5 times x minus 10, in other words, 5x minus 50. I could square both sides of the equation right now, but it might be easier if I first divide both sides by 3 to get the radical all alone. I know it looks weird to have a negative down in the denominator here, but don't worry about it. My next step is to square both sides, and when I square both sides, I get rid of the radical and get rid of any negatives. I'm squaring a fraction, so I square the top and I square the bottom. On the top, I get 5x minus 50 squared, and on the bottom, negative 3 squared is positive 9. What I now have is a quadratic equation that I need to solve. Generally, the way you want to solve quadratics is set it equal to 0 and kind of hope that it factors. Let's see what happens. If I multiply both sides by 9, I get 9x squared minus 180x plus whatever 9 times 116 is. Since this is my second time making this video, I don't want to make another mistake, so I'll pull out my phone. My phone claims that that's 1044. That's what I'd have on the left side of the equation. On the right, I need to expand out 5x minus 50 squared. So 5x times 5x gives me 25x squared. 5x times negative 50 is negative 250x. But if I'm thinking FOIL, both the O and the I in FOIL would produce one of those negative 250x's. So in total, I'd have negative 500x. And then the negative 50 times the negative 50 gives me positive 2500. I'm making progress. I want to set this thing equal to 0. So I'll subtract 9x squared from both sides, leaving me with 16x squared over here. I'll add 180x to both sides. That would leave me with what? Negative 320x. Negative 500x plus 180x. And then I'll subtract 1044 from both sides. which would leave me with 1,456. Fortunately, I think 1,456 is divisible by 16. I'm going to pull out my phone to confirm that. Yep, my phone tells me that's equal to 91. That's all sorts of good news. That means I got 0 equals x squared minus 20x plus 91 when I divide both sides of the equation by 16. And if I'm especially lucky, this will factor. And I think it does. That's kind of a miracle. Really, there's no miracles in math, but it feels like a miracle when I'm recording this video for the second time. I need two numbers so that when I multiply them, I get 91. And when I add them, I get negative 20. And because 7 times 13 is 91, I think the right side of this equation factors as x minus 7 times x minus 13. From here, it's easy. I got something times something equals 0. So either x minus 7 equals 0 or x minus 13 equals 0. So either x is equal to 7 or x is equal to 13. The critical values of this function come when x equals 7 and when x equals 13. Wait, two critical values? That's weird. Which one's my answer? Well, let's go back up to our diagram here. Remember, we're trying to figure out how far we should walk on the trail before we cut over and start walking on the sand. But remember, point A is only 10 miles west of point C. So it wouldn't make any sense to go 13 miles and then cut over. We'd be backtracking a whole bunch. So this critical value at x equals 13 doesn't make any sense. The critical value that's relevant in this problem is x equals 7. The optimal path to go from point A to point C is to walk along this path for a distance of 7 miles, in other words, x is equal to 7, and then make the rest of my journey along the sand. The question didn't ask, how far should I walk on the trail? The question asked, what is the least amount of time it would take me to get from point A to point C? I know the optimal value for x, and I also have a function that tells me the amount of time it takes for any value of x, t of x here. So all I have to do is take t of x and evaluate it at 7. T of 7 would be 7 divided by 5 plus the square root of 10 minus 7 squared plus 16 over 3. I've got the answer to the question, but if I've gotten this far, I might as well clean stuff up a little bit, right? 10 minus 7 is equal to 3. 3 squared is equal to 9. So I got 9 plus 16 under the radical here. 9 plus 16 is 25. So I got the square root of 25 over 3. Oh, that's awesome. I got 7/5 plus 5/3. My least common denominator would be 15. So instead of 7/5, I'll think about this as 21/15, multiplying the top and the bottom by 3. And instead of 5/3, I'll think about this as 25/15, multiplying the top and the bottom by 5. And what I end up with is 46 over 15. What? Just over 3. 3 and 1/15. Just over 3 hours to get from point A to point C. Is that reasonable? Well, I sure hope so. If I'm going 5 miles per hour, it would take me 2 full hours to get over here. If I had walked all the way over to here and then cut straight up, it would take me a little over an hour, right? Because I'm going 3 miles per hour and I got 4 miles to go. So if I were taking this inefficient path to go all the way to this point and then straight up, it would take me 2 hours plus another 4/3 of an hour, 3 and 1/3 hours. So the fact that my optimal time is less than 3 and 1/3, it's 3 and 1/15, is good news, and it certainly seems like a reasonable amount of time for me to go from point A to point C. I could probably quit this problem right now, and maybe I should, but I'm kind of a glutton for punishment, and I want to show you a little bit more. So for the visual learners out there, what I want to do is take a look at this function t of x equals x divided by 5 plus the square root of 10 minus x squared plus 16 all divided by 3. This function that tells me how long my journey will take based upon how long I stay on the trail. So if x equals 0, I'm taking a straight path from here to here. If x equals 10, I'm walking all the way over here. If x is negative, I guess it doesn't really make sense. If x is more than 10, I'm walking past this point and cutting back over. Let's take a look at this graph, t of x, using my favorite graphing program, Desmos. Here it is. I've copied that function exactly as we had it written on that page, and here is the graph that comes up. Does anything strike you as weird about this graph? The first thing to notice is if x equals 0, our journey is going to take us 3.59 hours. Okay, that makes sense. If I walked on the sand the whole way, it's going to take me a little while. And as x gets longer and longer and longer, the longer I spend on the path, the shorter my journey becomes. If I walk 5 miles on the path, my journey only takes me 3.13 hours. And if you look over here at 7, my journey takes me 3.067 hours, just over 3 hours like we calculated. And if you look really closely at that point, it appears that at 7 we have ourselves a local minimum. Yeah, that all makes sense. If I walk on the path more than 7 miles, it ends up taking me longer than this 3.067. right? If I'm on the path for 8 miles, it takes me 3.091. And if I scroll back out, what we see is that if you continue to walk on the path longer and longer, the amount of time your journey takes is longer and longer. Here's 10 miles on the path and the 3 1/3 hours that we predicted. And maybe even notice when you get past 10, you're really screwing up. The longer you spend on the path, more than 10 miles, is really going to increase the amount of time that your journey takes. That's all consistent with this picture, right? If you're on the path for 12 miles, you're looking at the point and it's kind of behind you in a sense. Big mistake if you're in a hurry to get to point C. Yeah, that's all right. I thought you said something was wrong. Well, remember, when we solved this thing, we found two different critical values. We found a critical value at 7 and a critical value at 13. What that means is the first derivative should equal 0 at 7 and 13. If we go back over here to this graph and we examine the point where x equals 13, we don't see a point where the tangent line is horizontal. And that's really surprising. Even though critical values could represent a local minimum, a local maximum, or neither, they should at least correspond with the point where the tangent line is horizontal. And clearly right here, it's not. Why? What's going on? What's going on is algebra. What's going on is we got two solutions here, 7 and 13 for this equation, but they're not both solutions. If we try plugging in 13 into the right side of the equation here, we get 1/5 plus 13 minus 10, in other words 3, divided by 3 times the square root of 13 squared, which is 169, and negative 20 times 13 gives me negative 260, and then I add 116. I know the suspense is killing you. 169 plus 116 is 285, and 285 minus 260 is 25. So I get 1/5 plus 3 divided by 3 times the square root of 25. I get 1/5. I get 1/5 plus 1/5. That does not equal 0. X equals 13 is not a solution to this equation. X equals 13 actually is not a critical value. And you're like, oh man, you made another algebraic mistake? Well, kind of. Really what happened in this solving process is we lost information. Where did we lose information? From this line to this line. Technically, and this is something that often gets overlooked in an algebra class, you cannot square both sides of an equation. Because think about it. Think if there was some value of x that made the left-hand side of the equation here equal to 5 and made the right-hand side of the equation equal to, I don't know, negative 5. Clearly 5 is not the same as negative 5. But if I square both sides of the equation, I get 25 on both sides. That's essentially what happened here. I'm not going to do it, but if you take the time to plug 13 into this equation, you'll see that it is a solution. But if you plug 13 into this equation, or this one that's equivalent, or this one, you'll see that it's not a solution. When we squared both sides of the equation, we lost a little bit of information in here, and that loss of information is what produced this second critical value. Technically, and I don't know if anyone really does this, definitely not any students, when one of the steps in your process is to square both sides of the equation, you should always check your answers. Because when you square both sides of the equation, you can lose information, and that loss of information could produce extraneous solutions, and that's exactly what happened here. So really, this function only has one critical value at x equals 7. It's not that the critical value at 13 doesn't make sense. It's that this isn't really even a critical value. Another way I can demonstrate that for you is by, instead of taking a look at the graph of the function, I can take a look at the graph of the first derivative. And if you take a look at the graph of the first derivative, you see that it equals 0 at this point where x equals 7, but it certainly does not equal 0 at this point where x equals 13. When x equals 13, the first derivative is 0.4, in other words, 2/5. In other words, exactly what we got over here when we plugged 13 into the first derivative. Anyways, I think that that's kind of interesting, but it's way beyond anything you need for this class. For this class, if you can represent time as a function of two variables, I'm impressed. And if you can use the constraint apparent in this problem to rewrite the function in terms of one variable, I'm really impressed. And then from here, you're taking the first derivative and setting it equal to 0 and solving. And if you make an algebraic mistake, kind of like I did the first time around, I'm really not all that worried about it. And if you didn't notice little subtleties, like the fact that one of these critical values is technically not really a solution to this equation because we lose some information, yeah, you shouldn't. But if you think that that's kind of interesting, I'm with you. I think that that's kind of fascinating, especially because most people would never understand what's going on here. Anyway, sorry for leaving you with such a hard example. Let's end this video here.